Hi guys, so in this video we're going to be talking about electrochemistry. So electrochemistry is defined as the study of the interchange of chemical and electrical energy. So the two type of cells that we're going to learn about a lot are galvanic or voltaic cells, and these are spontaneous chemical reactions, otherwise known as a battery, and electrolytic cells, and these are non-spontaneous and require external electronegative sources to get it started. So some things you have to memorize. Unfortunately, a lot of the other concepts we are able to just use math to prove, but in electrochem you have to memorize a few things. So one thing that you should know in galvanic cells only is the anode is where the electrode where oxidation occurs. So oxidation is the loss of electrons, therefore there's an increase in charge because there's less negative energy. The cathode is where reduction occurs. So you gain electrons, so you decrease charge because it becomes more negative. So electron flow is always from the anode to the cathode, and it's through the little wire. If you saw in the previous image, it's from the electrons are transferred through the wire. So a salt bridge is a device used to maintain electrical neutrality in a galvanic cell, usually filled with a neutral salt that'll split up into ions and balance the charges in each cell. So this is basically a little image again of what I just described. So the anode in this case is on the left. So the electrons are being transferred from the anode to the cathode. So the single line represents the phase boundaries, and the two lines represent the liquid junction. So here's the liquid junction, and the salt bridge is right here. So it's the anode to the cathode, and this is the voltmeter here, which measures the charge of the reaction, and also displays this energy. So one thing that you need to know is the standard cell notation, otherwise known as line notation, because this comes up a lot in multiple choice or even FRQs. So the way that this is written is basically a shorthand method. Instead of writing out this is the anode, this is the cathode. So we have here is that you have to memorize this kind of, is the anode would be the first thing you write. So the ZN is said it was here is the anode, so Zn, and then the anode solution is the Zn2 plus, because that is what is gaining electrons in order for it to become Zn. So it's being reduced. And then here we have the double lines to represent the salt bridge or crossing over to the next cell, half cell. And then we have the cathode solution, which is Cu2 plus, and that is gaining electrons, so it is being reduced. I apologize, the Zn2 plus is losing electrons, so I misspoke on the first part. So Cu2 plus is gaining electrons, so therefore it's becoming Cu neutral, so that's the cathode on this side of the standard cell notation. So next, how can we determine which substance is being reduced and which is being oxidized? So if it's not telling you it in the problem, then you have to look at something called a table of standard half reaction reduction potentials. So the more positive reduction potential is what gets to be reduced if you're trying to set up a cell that can act as a battery or a galvanic cell. So the next slide has this table. So as you can see here, this is the table that you'll probably get on a test, or even if you don't get this whole table on a test, you can use these. It'll probably give you the half reactions that you need. So as you can see here, these are really high standard reduction potential. So that means the F2 plus 2E minus to yielding 2F minus has a really high chance of being reduced as compared to a really negative value that would be really easy to be oxidized. So calculating E cell is what a lot of the questions will probably be about electrochemistry. So first, what you need to do is determine which element is being oxidized or reduced. So if you have this half reaction, which has a very positive E naught, versus a reaction down here like the Zn, which has a negative E naught, so you know that the greater E naught is going to be reduced because it has the highest standard reduction potential. So the next thing you have to do is the lower standard reduction potential is the element being oxidized. So you have to reverse the half reaction. So just flip the reaction, and just like any other things that we do when we flip reactions to the reverse reaction, you do the negative of that value that's given. So it would be the negative E naught. So you switch the sign of the reaction. And then what you have to do is balance the two half reactions, but do not multiply the voltage values. That's just one thing you cannot do. Don't multiply the voltage values. So you balance the half reactions by multiplying by, like if you have two electrons and one electron here, you're going to have to balance like you would a normal redox reaction. So then you add the half reactions together and the voltages you just add together. So the E cell is equal to the E oxidation plus E reduction. So which electrode is positive versus which one is negative is not on the AP test anymore. So that's usually really confusing for students because which anode, when the anode is positive or negative, switches between galvanic and electrolytic cells. So luckily they don't have that on the AP test anymore. So you can know it if you need to, if you think you need to, but it's okay if you don't because you won't need to know that on a test. So another quick fact is as a reaction in the galvanic cell proceeds, the energy decreases, which eventually turns to be equal to 0. So when E naught is equal to 0, the reaction has reached equilibrium, which means that the battery is dead and delta G is equal to 0. And it's proved by this equation here. So these are important equations for batteries. So we have delta G is equal to negative NF E naught. So the Faraday's constant is here, and it is 9.649 times 10 to the fourth. So that's just an important value to know, but it's also be on the equation sheet. And negative E naught implies non-spontaneous, because if it's negative E, then when you multiply the negative by the negative, you're going to get a positive delta G, which is non-spontaneous. And the positive E naught implies that it is spontaneous, so it's really easy to reduce. So it would be a good battery because delta G would be negative and therefore spontaneous, and that's what's favored. So another equation is delta G equals negative RT ln of K. So reactions where K is greater than 1 are favored. So when reactions are favored, that means that it's spontaneous. So delta G would be negative. So when K is greater than 1, the ln of K is positive. So therefore, the negative RT ln of K would be negative, therefore spontaneous and favored. And don't get confused between the constants. There's the gas constant, which is 0.0821. So don't get confused between those because R in this case is 8.315. Okay, one other equation that you should know is the Nernst equation, but this doesn't really come up that much. So when the cell is not at standard conditions, which it usually is, the E of the cell is equal to E naught minus RT over NF ln of Q. So Q in this case is the equilibrium constant at that point. R is the gas constant, which is 8.315, and the Faraday constant is F. Q is the reaction quotient, which not the equilibrium constant. So the reaction quotient is the products to the coefficient over the reactants to the coefficient. So E is the energy produced by the reaction. So that's the E at the non-standard conditions, but we have E naught, which is at standard conditions that you're given. And T is the temperature in kelvins. Don't make sure you don't have it in Celsius. And N is the number of electrons exchanged in the balanced redox equation. So favored conditions, like I talked about in the last few slides, E cell is greater than 0 because when you use that equation, you get that it would be spontaneous because delta G is negative. Obviously, when delta G is negative, it's spontaneous, the second point here. And K is greater than 1, the reaction would favor the products. Therefore, it would be more spontaneous. Thanks for watching, and I hope that helped with electrochem. The next video, we'll be talking about electrolytic cells. Thank you.